My name is Pedro, and I'm going to be showing you some of the work I've been conducting as part of my PhD at the University of Tromsø, the Arctic University of Norway, as part of the research project Climate Observatory for the Arctic Tundra, with the title Incorporating Sampling Error in the Estimation of Autoregressive Coefficients of Animal Population Cycles Using Capture-Recapture Data. My name is Pedro, and I'm going to be showing you some of the work I've been conducting as part of my PhD at the Hello, everyone. Thank you for joining this session. My name is Pedro, and I'm going to be showing you some of the work I've been conducting as part of my PhD at the University of Tromsø, the Arctic University of Norway, as part of the research project Climate Observatory for the Arctic Tundra, with the title Incorporating Sampling Error in the Estimation of Autoregressive Coefficients of Animal Population Cycles Using Capture-Recapture Data. So I can see that this title is a little bit long, and because of that, I'm going to focus on some of the keywords in the title and use them as a template for the rest of the presentation. So now let's focus on the first word, population cycles. Let's assume that we are following a population over time. We are interested in this population, and we are interested in modeling how this population fluctuates. So let's assume that the population process is then defined by an autoregressive process, which constitutes the true process that we want to estimate. And if we are interested in this population, we first are going to need to sample from it. And let's say then we set up a capture-recapture experiment, and we obtain some capture-recapture data from this population, which will give us some information, not only on the number of individuals, but also on the capture process. But so what we see from this data will not necessarily correspond to the true underlying process. And the difference between what we see and the reality will correspond then to the sampling error, which we will want to account for if we want to properly estimate the underlying autoregressive process. And so this is exactly what we want in this study. So I'm going to particularize in a case study with some of the data that I work with. And being here in the north of Norway, in low Arctic and Arctic ecosystems, some of the most important animals that we can study, and some very iconic animals also are the rodents. Here seen in the mouth, a gray-sided vole seen in the mouth of an Arctic fox. So both voles and lemmings are very important to these systems. They help predict the whole system, as they play such an important part in everything from vegetation to predators, and are even correlated with abundances of different species. So by modeling the populations of these animals, we get a better understanding of the system. Lemmings are really hard to estimate. They are very unpredictable, but gray-sided voles are not. And in particular, they show these very well-marked cycles, which show some very strong density dependence, in which the number on some years is very high, and then in other years, it completely crashes. So we have peaks and crashes interspersed more or less with a 4 to 5 year periodicity. And this is the type of data that we are interested in working with, and this, we want to actually estimate these population processes. So the typical way that we can use to estimate these processes, and the most trendy and current way, is through state space models. And state space models are defined as first having an observation model, which describes the sampling process. And here we can assume some sort of Poisson or log normal distribution for the counts or the log counts. And then this observation model then is linked to the process model, which describes the process of the population fluctuations. So in the case of the voles, it's assumed in most of the cases that they follow autoregressive processes. But these state space models carry an issue, because usually we have to do some sort of broad assumption, and we have to assume some sort of homogeneous capture process. And if we actually want to include an explicit link to the capture process in the case of having heterogeneity, that is, in the case that different animals respond differently to the capture process, then we cannot actually include an observation model. I'm going to particularize this to the case of the voles. Let's assume that big voles are more easily captured than small voles. And here I represented a 2-day capture-recapture event in which some voles are captured only on second day, others only on the first day, and others are captured on both days. What we will want to account for is for the voles that are never captured. And in this very simple scenario here, I have the tiny voles which were not captured. Here we essentially end up with a multinomial likelihood where we have different capture histories being different categories, and there is one which is completely unobserved. So this will lead us to a conditional likelihood, and we cannot have this conditional likelihood in a state space model. So with this work, we actually wanted to try to include an explicit capture model in our observation model. And to do this, we could not do a state space model, but we did something similar, although not integrated, as in a stepwise approach, where we first modeled the capture probabilities of our voles as a function of covariates and random terms. So we first modeled capture probabilities of our voles. In reality, we modeled the capture histories, frequencies, and from that, by making some assumptions through the multinomial likelihood, we can then estimate the capture probabilities, and through the very well-known Horvitz-Thompson estimator, we can then get an estimate for the number of individuals at a given point in time, using the probability of them not being captured at all. And so by having this estimate for the number of individuals with time, we can then fit an AR2 model to this time series. And then an AR2 model, which is a model which is considered to very closely approximate these sort of processes, has then these very two important coefficients. One, the phi1 here, linked with the direct density dependence, so with the number of animals present at time t-1, and then the delay density dependence associated with time t-2, and together with a process variance, which will regulate the whole fluctuations variability. So then we were interested in understanding how important is it to include capture history information in the estimation of this density dependence of these AR processes. So we set up a simulation study in which we base ourselves on a concrete and real data set. So we assume that we have an AR2 population, and we set up a capture-recapture experiment over 20 time points, a very short ecological time series. And we had a capture-recapture setup with 2 sampling days, so exactly like how I've been showing so far. And we had these capture probabilities perfectly depending on the weight. In reality, we know that a lot more variables affect capture probabilities, but let's keep it simple here, and we are assuming that we can perfectly estimate the capture probabilities, or at least we know perfectly which variables describe that. So if we take that into account, how well do we estimate the AR2 parameters with different methods? And that is, with including capture history information and with disregarding capture history information, or even assuming a more homogeneous capture process. So that's exactly what we did in our simulation study. So here on the y-axis, we have the phi1, the direct density dependence coefficient, and then the phi2. And then we test for a bunch of different combinations of parameters. Let's say here on this point, we have phi1 equals to 0 and phi2 equals to minus 0.8. And then we try to estimate how well can we estimate these individual combinations using different methodologies. So here the first one I'm showing is the baseline, which is if we actually knew the true number of individuals at each point in time. And the second one will be the raw counts. So if we disregard capture history, we just look at the observed counts, how well would we estimate it? So then using the multinomial likelihood and estimating capture probabilities, how well then will we estimate? This is now given by the red point. We see that we improve quite a bit in some scenarios more than others. And now what if we make an assumption of a homogeneous capture process through a Poisson process? So we fit the Poisson process to the counts. We see that actually it's not very good, and for this case, it actually performs worse than just using raw counts. But then we thought, well, what if we perform the Poisson process on the multinomial corrected counts? So in that case, we see that we actually improve the estimation process quite a bit, especially in some cases more than others. So, but now I want to tell you to notice that this is only for a process variance here for this epsilon term of 0.08. What if then we vary the process variance? So now I'm going to show you results for different process variances. So I'm starting with 0.04, and we see that the differences in root mean squared error are quite big, with the Poisson process methods performing worse than the raw counts and then the multinomial. When we start increasing the process variance, we see that the methods start getting closer to each other. In particular, the Poisson on the multinomial starts approaching the multinomial one on the raw counts. And then as we further increase, we see that they tend to converge. So although the methods, including capture histories information, perform better, here the yellow and the red, they actually don't perform that much better compared to the ones disregarding that information. So, and here on this plot, I'm showing you root mean squared error, which means that lower is better. So now, to conclude, so on this study, we use the stepwise approach to try to account for individual heterogeneity in density dependence estimation. So to account for this information in our observation model, and because of that, we could not use a state space model. So the importance of explicitly modeling this information then becomes dependent on the parameters of interest. So it depends on the phi1 and the phi2, the density dependence parameters of the processes, but it also depends greatly on the process variance. So if we have very high process variance in our case study, which is usually not the case with vol populations, then we see that actually we don't gain so much by explicitly modeling heterogeneity. So a state space modeling approach, including an explicit link to the capture model, would be the ideal approach, but which we are not sure of how we would be able to implement considering the conditional likelihood. I would like to finish by saying that this work has been accepted for publication in Ecology and Evolution and is now under review process. Thank you very much for watching, and I hope you enjoy the next talks.